We're going to start now with the first technical session, and we're going to have our first plenary lecturer, and we're very fortunate that Dr. Christoph Richter can be here to give us a talk on the status and perspective of CSP at this time. Dr. Richter's got a PhD in physical chemistry at the University of Cologne in 1993. He joined the DLR, which is the German Aerospace Centre department at the Plataforma Solar de Almería in Spain in 1994, which is the major test centre for R&D in concentrating solar high-temperature technologies. He started as project manager in the solar chemistry area on research projects regarding photochemical applications of solar energy for water purification and fine chemical synthesis. Currently, he works on different aspects of solar thermal power plant operation, including thermal storage, cooling, and environmental impacts. He is also responsible for the administrative and infrastructure department at the Plataforma for DLR, and since 2008, he is the executive secretary of the International Energy Agency's implementing agreement for CSP called Solar Paces. And I can also tell you that he is a very, very good friend in South Africa, and this is already the second time this year that he's in South Africa, and there's a rumor that he's coming back for an extended stay at Stellenbosch University later this year. Dr. Richter.
Yes, good morning, ladies and gentlemen. Thank you very much, Vikus, for the very nice introduction, and I can tell you all that I'm really happy to be here now for the second time this year, and really preview to be here for another third time, because it's a very nice country, a very nice region, and it has such a high solar potential, especially for the technology concentrating solar power that I've been working for during a long time now, that it's a good occasion to come here and look more into the potentials, possibilities, and support the process here in South Africa. And I would like to give you a kind of broad overview in the next, say, 45 minutes or so about what is the situation of CSP, what is the perspectives, and would like to start here to show you shortly the outline. I will just give a brief introduction into the CSP characteristics, highlight some examples of the current market situation, mainly in the main current markets, Spain, US, and the European, Middle East, North Africa region where the Desertec vision is under realization now. I try to give you a short overview of some important R&D activities in this sector and resume on some perspectives of the, let's say, social, also economical benefits and the long-term perspective. You see here already one graph of the IEA which shows the results of a roadmap. I will go into this with a little bit more detail at the end of the presentation. So just a short description of the main characteristics, just to remind how does thermal power works. You have here conventional power plants, e.g. based on coal or maybe nuclear, that produce heat, produce then steam in a steam cycle, run a turbine, produce electricity, and in most of the steam cycles, or in all steam cycles, you need some kind of cooling to have a closed cycle and turn this back into the turbine system. Now, the difference to concentrating solar power is in principle very easy. You just replace the conventional fossil fuel by solar energy. In this case, you use concentrating systems like this parabolic turf mirror that you see here, or this power tower that concentrates solar radiation to in a degree of, say, about 100 to 1,000 times and produce temperatures in the same range that you find in conventional power plants, and then basically run the same process. Of course, then there are details that are not exactly the same, but this is one of the advantages and some of the interests also that the technology has to potentially upgrade existing power plants or just fitting well into a given national grid system. Just a few remarks on the early beginnings. Concentrating solar thermal technologies are quite old, definitely much older than, for example, photovoltaics. A famous myth, I would say, says that Archimedes already used it to defeat Syracuse from the attack of Roman ships by burning the wooden body of the ships with concentrating solar radiation. It wouldn't have worked like this, I would say, but it's an interesting first beginning. Then it went on with some different efforts. One person to be named here is the French engineer Augustin Mouchot, who already had some dish-oriented steam engine devices on the exposition in Paris, I think in 1860. And one of the, let's say, last attempts in the younger history was a first parabolic trough built in Egypt from the American engineer Frank Schumann, who used this device to produce steam directly in the focal line to run a steam engine to pump water. The interesting fact about this is also that this was built in Egypt in 1912 because at that time they were importing coal from England. And of course it could seem a little bit contradictory not to use the solar resource in Egypt. This worked quite positively during a few years, but then First World War and the discovery of cheap oil made a first finish to this first attempt of concentrating solar power or concentrating solar technologies. And I will give you on the next slide a short overview on the typical basic configurations that we are looking at. We have, let's say, we talk about linear concentration systems that you see here in the upper part of the slide, and about point concentration systems. Linear concentration systems typically have a concentration range of solar radiation about 100 and can achieve operating temperatures of about 500 degrees Celsius. Point concentration systems, because of the higher concentration factor, can go up to a ratio of 1,000 and maybe more, and can achieve temperatures also of 1,000 degrees Celsius and more. The most typical and the most mature technology right now are the so-called parabolic troughs. You can see here the parabolic mirror. You can see the tube through which normally a heat transfer fluid is circulated. The temperatures here are about 400 to 500 degrees, depending on the thermal fluid system. And this is then delivered to a heat exchanger to produce steam and to produce then in the next step via turbine power. Variation of this system could be considered the linear Fresnel system, where you have kind of sliced the parabolic trough, the parabolic mirror, into long segments that are built closer to the ground, and that each one moves individually to track the sun and to concentrate on this absorber tube, which is fixed on a certain point in the Fresnel system. This has the advantage that the mirrors can be made from basically flat mirrors. In the parabolic trough case, they have to be bent precisely to a given shape. The absorber tube is fixed here. In the case of the parabolic trough, it moves and with the sun, because all these systems have to track the sun. And that gives you because of the moving absorber tube, you have more technical challenges with the connections with ball joints or moving connections here, which you don't have in the Fresnel system. Therefore, the installation costs of Fresnel systems are expected to be lower. And on the other hand, you also have to take into consideration that the optical characteristics of both systems are different. In the parabolic trough case, the orientation towards the sun is basically the same during one day, and that gives you a more flat operation curve during many hours at midday when the production is more or less stable. In the Fresnel system, you have much more steep curve at midday when the sun is up on the mirrors and the orientation is optimal. But when the sun goes down, the effective mirror area, which is usable for the receiver tube, gets smaller, and therefore you have a very steep curve and you need more storage or more hybrid firing to integrate that in a power cycle. So the question which of the systems finally will be better or cheaper, I think can only be answered during the experience of more Fresnel systems installed, which is currently undergoing in some countries. With the point concentration systems, you have on the one hand the dish engine system, which is single modular units that track the sun in two axes and concentrate on a receiver of typically a Stirling motor that converts the thermal energy into mechanical energy and then electricity. The more widespread systems now in the point focusing systems are the solar towers, where you have a fixed receiver high up on a solar tower in maybe a height of between 80 to 160 meters are currently realized systems, and a heliostat field that tracks the sun and reflects and concentrates on top of the tower to achieve high temperatures to drive different processes not only power generation, but also chemical systems for example, hydrogen production. Okay, this is a short overview on the technical configurations. We will see some more examples in the next slides. But first, here are some pictures. This is a parabolic trough at the Plataforma Solar de Almería. This is one Fresnel system that has been built there. You can see here the mirrors and here the receiver irradiated. This is a parabolic dish, also in Spain at the Plataforma Solar de Almería. And this, again, in Spain, is the experimental tower at the PSA, the Plataforma Solar, where you can see here the mirror field and the tower where radiation can be concentrated. Now, one important point of CSP systems is also the ability to store the thermal energy that has been produced in the first step by concentrating solar radiation. Let's say the typical hours of nominal operation capacity of a solar system of this kind are about 2,000 hours per year. When you add thermal storage, for example, in form of molten salt in such tanks, that you can heat up with a higher solar field, with a bigger solar field, then you can add another 2,000 hours or even more, depending on your layout of the storage system, and therefore achieve more operation hours or shift the operation hours of such a system to better meet the demand curves and also to have potentially better economic performance of the whole system. This is briefly shown or indicated in this graph. Normally, with integration of a storage system, you have a minimum of the generation cost because the storage system, for example, allows you to better use the power block of your power plant, which is also an important part of the investment. If you have pure solar operation, then it's only used in the order of 2,000 to 2,500 hours. If you integrate a storage system, then it can be used longer, and therefore you normally get better overall cost of the system. You can also, of course, hybridize concentrating solar systems, feeding heat from natural gas burners into the system and therefore also extend the operation hours. One typical configuration, which is right now, I would say, the most configuration, which is built in Spain in many plants, you see in this picture. You have here symbolized the solar field with many parabolic troughs built in lines. And you have here in this red system the heat transfer fluid, which is normally thermal oil. So with this you drive the steam cycle here. And then you have integrated a storage system which consists normally of two big tanks. I will show you a picture a little bit later, which contain molten salt that you can operate, in this case, in the temperature range between 300 degrees Celsius in the cold tank and about 400 degrees Celsius in the hot tank. And this is heated up by the thermal oil from the primary solar field. And then, if there is no sun available, you can take heat from the hot salt tank, drive it through the system, generate steam again, and operate the steam turbine. This gives you the important value of dispatchable power, which can be in the future also an important contribution of concentrating solar power to, let's say, stabilize a renewable energy system with a high degree of fluctuating renewable energies that need some kind of backup from other systems. Okay, a short overview on the global CSP development pipeline that we have now. This is a picture made from GTM research that shows you projects under construction or development worldwide. And I would just like to point out that currently, as I said, the main markets are Spain and the US in the next years. But as you can also see, all over the world, mainly in the Sunbelt countries, there are efforts underway to already with started construction, with projects under development. Also, India and China have big programs. South Africa, of course, here also. On the other hand, these numbers are, it's a dynamic process. These numbers are not always up to date. I think South Africa has already more projects under development, and I think we will hear more of that in the conference in other presentations. But this gives you the idea that from currently about 2 gigawatts CSP in operation, we expect to be at about 20 gigawatts towards the end of this decade, towards 2020, which will certainly also contribute a big part to cost regression in this technology. And now I would like to give you some examples from Spain. as basically right now the most important market for concentrating solar power. Here is a picture of the first two solar power towers that have been built by Abengoa, by the Spanish engineering company, near Seville. They have a big site there where they build different plants. This is a 20 megawatt power tower, and this is an 11 megawatt tower. They operate with steam, with a small storage of only half or 1 hour, which is a pressurized vessel. The plant surface is 60 to 90 hectares. And they operate with heliostat systems with mirrors that have an area of 120 square meters and were commissioned or started operation in 2007 and 2009. The PS11 was the first one. And here is one picture how it looks in operation. This is PS20. You can see here a little bit of the concentrated solar radiation entering the receiver. And this is a view on the solar field where all these mirrors reflect radiation onto the system. And you have here the power block and all these issues that are normally built near the central receiver. Fresnel is another system that has been now installed in 1.4 megawatt, was an experimental system or pilot system in the province of Murcia. They are now in operation to start up a 30 megawatt Fresnel system. So this is up to now the biggest Fresnel installation that is in operation or in first operational phase. And they produce steam directly at a temperature of about 280 degrees Celsius with saturated steam operation. This is the company Novatec from Germany who has been built this. And then is one important, I would say, new solar tower that has come into operation last year in Spain. It's the Gema Solar Tower, built by the Spanish company Torresol Energy with about 20 megawatts. It has a round field, as you can see here. And it has, for the first time, 15 hours of storage capacity integrated using a molten salt heat transfer system here at the top of the tower, which directly integrate the hot salt into the heat transfer fluid system. So you heat up the salt here up to about 560 degrees, produce then steam in a heat exchanger, and because the hot salt can be heated up to quite high temperatures than, for example, thermal oil, the storage system, because of the higher temperature difference, can store more energy in a given volume and a given mass of salt, which makes this more cost competitive in this point. And this plant is operating now since about 1 year, and from what I've heard, it's operating quite successfully, especially the storage system is very positive. The most typical configuration you have in Spain here is one example of the Iberdrola plant in Puerto Llano. Is the parabolic trough plant with a size of 50 megawatts. Typical dimension for this area is about 1.7 to 2 square kilometers of space. And a big share of them integrate thermal storage. This one is an example which does it not. And I will show you now also one picture of the 3 undersol plants, which have been the first to be developed in big part from the German company Solar Millennium, built by us, the Spanish construction company ACS and Cener, the undersol plants 1 and 2, and undersol 3 is now under startup from a German consortium. And they integrate this storage system for about 7.5 hours of storage, nominal operation of 50 megawatts without sun. And the dimensions of this system are quite impressive. The tank for this has a diameter of about 36 meters and a height of 14 meters. This is similar to a Spanish bullfight area. And it's filled once with a mass of about 30,000 tons of molten salt. And then you use this in this cycle that I've described before and can deliver solar electricity from solar energy even in evening and night hours, or use it to stabilize the operation of the turbine system and so on. And the operation experience with this, which has been reported, is very positive, and it can be considered as a quite mature storage technology also in this system. Okay, just to give you an overview on the breakdown. Right now we have 1,223 megawatts operating in Spain, and another 1,200 are expected to be finally constructed or finished until end of 2013. Of this, the big share is parabolic troughs, and only a fewer part are the newer systems, towers and Fresnel, and a few systems on steering technology also. And 62 of this include storage in Spain. These are data that have been provided from the Spanish association Pro Termo Solar, which is active in supporting the solar thermal market in Spain. And this is the breakdown of the plants which are operating currently. Now we have 3 central receiver plants which make up to 50 megawatts more or less. The Fresnel are about 30 megawatts. Sterling is only a small portion with more experimental systems, and the big chunk of all this are 23 parabolic trough plants with about 1,150 megawatts. This is the situation in Spain. It has been extremely dynamic in the start since, let's say, 2004, and very much of activity and building in 2008 to 2010. Unfortunately, during the current economic problems in Spain, the government has now made a moratorium, a stop to renewable energy installations. They want to start again, but right now there's kind of a standby position in this market, and developers are looking much more also to US and to other markets like, for example, South Africa. But of course, it has built up a big part of capacity and potential in Spain, which is now available for the further development of this. In the US, you have here a breakdown of CSP plants which are currently operating. I don't want to go through all details of this list. You have here the big part of the plants which have been built in California, the solar electricity generation systems, already starting in the mid-80s, and which have been during a long time the main, let's say, testimony for the maturity and operativity of this technology. They are still in operation, some of them now more than 25 years. A few big plants that have been built in the last years are, for example, the Martin plant in Florida with 75 megawatt, and Nevada Solar One with 64, and some smaller trough plants that have been finished now. Some of them have more experimental character. For example, the Saguaro plant is an organic Rankine cycle plant that is operating for experimental purposes. And this gives you also the, there is one tower operating now with 10 megawatts in the plant from BrightSource, Coalinga. And there are some other big plants now under preparation, under construction, that build big power systems that I will show you in the next slide. This is an overview of plants that are now under construction in the US. One important observation that you can make here, I think, is that the unit size of this plant has grown quite a lot since the first, because for example, the first plant built in California, the SASEC plant, the biggest one, had 80 megawatts for one unit. Now they build plants in the order of 250 to 280 megawatts, one unit, one power block. And this concentration on a more higher capacity power block also gives a big improvement to the cost situation and the cost regression of the systems. But also they are building, especially BrightSource, is building a large tower system which consists of 3 single towers operating with steam at about 480 degrees, and with a total of 400 megawatts, nearly 400 megawatts, and this is right now the biggest concentrating solar plant, and I think the biggest solar plant anyhow under construction. And the single unit of this is 120 megawatts, so there are different options for the size of solar towers. And I would just like to show you in the next slides a few photos from this that have been provided to me from UL Gila and from BrightSource. Here you see the construction area of the 3 plants with part of the tower under erection, and here you see already part of the heliostat fields built. Here are a little bit more details about the construction work of the tower system. And finally, also a view onto the heliostat system. These are heliostats. I actually don't know the exact dimensions, but they're not very big, but they cover the area very closely, so they concentrate very well the technology on a relatively small surface. And there is a lot of engineering and development in how to control this big heliostat, this big mirror field, to achieve on a big receiver where you produce steam on different areas of the receiver the right temperature at this point to guarantee a stable steam production. And this is one of the technology challenges that is in the system, definitely, but which can be solved nowadays, for example, much easier with computing power much cheaper available than it would have been possible like 25 years ago when the basic ideas on these systems were already available. Now, this is a view on the US, and I would like to show you in the next slides a little bit of overview on the development of what we call the Desertec vision, the idea that in general the potential to tap the deserts on Earth and use the solar energy that is very abundant here available for the supply to the local communities, of course, firsthand, but also for export to nearby centers of demand that can use this as a second source of electricity, of power for their own demand. And this picture shows you also very nicely how abundant, in principle, solar energy is to fulfill the demand of mankind, because this big spot here shows you the area that would be required to produce all the electricity that is required by mankind, by the whole world, in the year 2005, for example. It is in the order of about 2% of the Sahara surface. So you see that the potential is huge to fulfill basically all needs of mankind with solar energy. And now there are, based on this vision, which has been already formulated in the 30s and which could be also was studied to be used via hydrogen as a transport vector for energy, has now got more impact. The Desertec Foundation has been very active in promoting the idea, and 2 years ago in Germany the Desertec Industrial Initiative was formed of many big companies, also banks who started to believe more in this business and who are now promoting specific efforts to create the necessary framework to realize the necessary transmission grids and to realize first pilot projects. Let me show just in the next slide a little bit more how this vision looks. It's not only solar, it's also the idea is to build on the wind power that you have, especially, for example, on the Moroccan coastline, to use this for the local demand and to also build up a transmission grid that would be capable to close a ring of electricity supply in the North African, European and Middle East area. And by this way, using the renewable energy potential over a large region, also contribute to balance the fluctuations that you would have locally. For this, they consider relevant technologies, field-proven technologies, which are CSP, PV, wind power, and high-voltage direct current transmission. All of these technologies are available for the market. I don't want to go through all the details on this slide here. Just showing you that is the main challenge in the realization of this is more the finding a political stable framework to guarantee to investors the security of their investment, which has been estimated by colleagues from DLR to be about 400 billion euros up to 2040, to build up a system that could supply up to 15% of European electricity demand and fulfill the demand, of course, of the local population, also for desalination and other purposes where they have a growing demand for fresh water in the coming years. This just summarizes a bit some of the main pros and cons of the different technologies. Just looking at CSP, what I said, it's dispatchable with storage, but it needs direct solar radiation, and it's very well combinable with conventional power plants. Until now, it is still not in the same range of development as PV, for example, but it's gaining a lot of momentum in the last years. And with this, I would like to switch over to give you some overview on current R&D activities that we are working mainly at DLR and in other research institutions to support the market development right now. This is mainly the first point here, the development of quality assurance methods to guarantee that the plants really perform at the capacity that they were designed for, that they are expected, and work on new fluids that can operate at high temperatures, new cycles, operate on different new storage systems, which is a very important part, and solar fuels, like generation, for example, of hydrogen from solar radiation, from concentrated solar radiation, and water directly by thermochemical water splitting processes, and let's say, to give the highest possible penetration of solar energy into the future energy mix. First, a few examples for what we call qualification developments, quality assurance. Here you see an example about the numbers that you need for a solar field for 50 megawatts of electricity in Spain. These are 624 single 150 meter long collectors and 7,500 modules. It gives you a total aperture area of the mirror field of 500,000 square meters and many mirror support points, bearings, absorber tube supports, many technical details that need to be aligned with a very high precision to achieve finally in the tracking of the sun a 0.1 precision to really match the receiver with the whole solar radiation available from this concentrating system. If there are failures that are higher in these structures, let's say of more than 1 millimeter in a structure of typical size of 6 meters width by 150 meters long, that will lead to growing losses in efficiency and therefore make the economics of a plant very much worse. And therefore the interest of industry companies also to receive systems to guarantee the quality. And one of the systems that has been developed is based on photogrammetry. You put a lot of marks on such a mirror surface. You take a number of digital photos from different positions, and from the mathematical evaluation of this method, then you get a picture how the shape of the collector is compared to the ideal perfect shape, which is here shown, of course, in an exaggerated version. And that, again, gives you, let's say, in the development of such a collector structure, the idea where you still have flaws, where you still have to improve maybe the stiffness of the structure or the mounting of the facets. And it gives you a better tool to know exactly the precise shape to evaluate the performance of the collector and later on also the whole plant. And this has been also developed to a fairly automatic method that you can use during the mounting of the collectors. When you mount in series lots of collectors to build in the field, to guarantee that there are no systematic errors which would be much more costly to correct later if the collectors are already in the field. Another method that has been used here, or this is used to control the quality, is to measure the radiation that achieves the receptor here, this absorber tube, and to compare it with ray tracing and use this also to derive information on the exact collector shape and improvement potential. Another tool that we have recently installed at the Plataforma Solar de Almería is a rotary test bench specifically thought for parabolic trough collectors. The main characteristic is that you have a system that is completely completely tracking in 2 axes. It can follow the sun here in an azimuth angle of 340 degrees, and it can also in the elevation. In the elevation, it can also track the sun during the whole angle, and that means that you can use or can have this component follow the sun perpendicular during a whole day, and that makes the evaluation of the performance much easier, much more precise than it would be if you build it in a collector that is fixed mounted in one axis. And it can operate under different conditions here, and it is used now already by some companies to make studies, for example, on absorber tubes, on new mirror facets and such things. So we see that it's a good tool that helps the market to develop and to achieve also the goal of further cost reduction. Now, as one example for the development and search for new fluids, we have been working for a long time on the replacement in this system that I've shown you before on the primary heat transfer fluid, which is normally thermal oil, and to realize direct steam production in the absorber tubes, which is a quite straightforward idea, but you have to take in mind that, or you have to have in mind that for the operation of this cycle, typically you want to have steam temperatures of 400 degrees Celsius, 100 bars or more. So it requires some more engineering on the tubing systems and so on. So there are challenges compared to the basic idea to make it easier. But this is of course, the scheme of what you would like to achieve, to just save the whole primary cycle, which would also allow to go to higher temperatures, up to 500 degrees, and make the whole system easier and make the conversion efficiency higher. And this has been built at the PSA, and in this parabolic trough of 500 meter length operated during the last about 8 to 9 years, with now 15,000 hours of operation. You see here one scheme of the system where you feed in water, produce steam, then you have here a water steam separator, and you overheat the steam only on this last short portion of the collector to make sure that really only overheated steam comes to the turbine. You have no problem with water droplets, which are fatal for turbine operation. And there were some developments on steam separators. So this is now at a stage where we are looking for a pilot operation or pilot demonstration, and to combine it with a well-fitting storage system for steam production. Another research line of DLR is solar gas turbines. I have only here one screen that shows you the basic idea. If you look at the annual efficiency from mirror surface to electric, and from solar radiation to electricity produced, it's about 16% in a Rankine cycle, which is the typical system for parabolic troughs. Because of the limits in temperature, if you go to modern gas turbine systems and put it into a combined cycle, then we expect from studies that you can achieve up to 25% annual electricity production. And this increase in efficiency over the year should allow you to save a large portion of the solar field, which is symbolized here by this brown part, which is not used any longer, and therefore contribute to the cost reduction of the system. Also here, experiments have been made at the PSA. You see here the concentrated radiation on the entrance of a solar gas turbine, which has a pressurized vessel, of course, to be able to operate a solar gas turbine with hybridization. I am not going into the details, but I think we will have another presentation from my colleague here, which highlights some of the specific details of solar gas turbine systems. Another effort, just with one slide, is development of storage. In this case, phase change, because phase change, using the phase change from liquid to solid salt or another solid material, gives you a lot of energy storage capacity in relatively low mass of storage material and relatively low storage volume. We have been developing a system here that uses a sandwich structure of graphite or aluminium, where the molten salt has a high surface of heat exchange, and which has been used here in a 700 kilowatt hour storage system in a conventional power plant, combined with a small parabolic trough in Almeria, also in Spain. And this is now going to a further 30 megawatt hour demonstration system in Germany, funded by the German Ministry of Environment, to make also this phase change storage system available for the market, which would be an important part of a direct steam production system. Now coming to the, let's say, more future applications. This is one example how we can produce hydrogen as an energy vector, also as a fuel for transport vehicles, using water and concentrated energy. Just very briefly, you have here a reaction bed that shows you that is packed with a catalyst system. You feed hydrogen steam into the system, irradiate it and heat it up to about 800 degrees Celsius, and it's split. The oxygen is absorbed in this system at this point, and hydrogen is released. And then in the next step, where you can switch the heliostat field configuration, you can heat up the same catalyst system to about 1,200 degrees. Then the oxygen is released again. So you, let's say, recycle the system. And by this, you can build up a so-called thermochemical cycle for, in this case, production of hydrogen. This has been tested in two reactors in Cologne and at the PSA, 2 identical reactors, so that each one can, at the same time, work at 800 degrees Celsius or 1,200 degrees Celsius. You can switch between those, and you are able to produce a more or less constant flow of hydrogen. So, another example of chemistry applications is the production of syngas, which has been done by a Swiss group, using carbonaceous materials like sludge or even plastics, biomass, which is fed as waste carbonaceous materials plus hydrogen steam into a solar gasification system that you see here on the right side. You have here the feedstock, you feed in hydrogen, you enter with solar radiation, and you produce syngas, a mixture of hydrogen and carbon monoxide, which is an important feedstock in general for the chemical industry, for many other bulk chemicals, but you can also use it as a storage system or use it, for example, in this case, one of the addressed applications was cement production, where you need high temperatures, but at a constant level. And therefore, you need a kind of intermediate storage system, which could be syngas in this case. This is only a brief resume from our Swiss colleagues, and there will be a more detailed presentation on this at the next Solar Paces conference also. But it shows you a little bit of the width of potential applications. With this, I would like to show you one important project that has been started, or this is in the starting phase in the European Union now, and financed by the European Union with the idea to increase the R&D capacity in increasing the potential and building up a new, maybe virtual, concentrating solar power research center. This has been initiated by the Spanish Andalusian Center for Technologies and Advanced Energy Research. The main point will probably be built here near the PSA, with participation of many partners, also DLR, French CNRS, the Israel Weizmann Institute, 2 Portuguese participations, Enea from Italy, 2 groups from Greek, and also 2 universities from Turkey, and the Cyprus Institute. Cyprus is also entering into Solar Paces and also entering to use concentrated solar energy. And this is now a project which is going into the preparatory phase to define, on the one hand, technical characteristics of upgrade of existing facilities or building new facilities that offer more and increased capacity to the research communities, and also define, which is an important part in this kind of preparatory, ESTELA, the European Solar Thermal Electricity Association, is also participating in this. So to upgrade the existing facilities with a budget, if this is realized in the end, which is about 120 million euros, that gives more access and better access for industrial partners, for research partners, and to have optimum scientific capacities for research and development in this area. It is now under negotiation for the final contract for the preparatory phase, which will take 4 years, and this will define the details. And then in 2016, if everything goes well, then the detailed construction of such a increased facility will start. These are the main aspects of what will be studied in this proposal now: the financial sustainability, the governance and legal status, the access for user, and also e-infrastructure. For example, if you have research groups that are not necessarily at the same site but are running their system there, that they could have direct access to see the data and operate the system via internet, for example. Okay, a short overview also on the Sunshot initiative of the US. I will be quite quick because actually I see I'm running out of time. That is aiming with a big structure to achieve a very ambitious goal, namely to decrease the current in US cents, about 0.21 US cents per kilowatt hour, through different measures and different programs, to about 6 US cents by 2020. to efforts in manufacturing cost, collector efficiency, and new conversion cycles. This is the goal, and these are different accesses. Solar field receive a power block, the heat transfer fluid, which are addressed in the Sunshot initiative, another program, Muriel Hot, and a specific activity also on storage development. With a quite big budget, only the Sunshot initiative has about $60 million over the next 3 years to work on these goals. And here you see a breakdown of the award portfolio in the different areas of collectors, reflectors, engines, and heat storage. And you have here also the many companies and institutions who participate in this. So you see it's a very broad initiative to promote and to increase the cost competitiveness of this technology and to go ahead with this. This shows you the breakdown on laboratories, universities, and industry in the first diagram, and also the breakdown on the different technology sectors in the second breakdown. You see always there's a very high concentration on storage and also a very high concentration on tower systems, because they are normally considered as having the best potential for long-term cost regression. A short remark also on a study that has been released by NWEL, which shows you that in an electricity system with a high share of fluctuating energies, like for example PV, at about 20% PV you can come, or wind also, you can come to a situation where in summer months with not very high demand, you have to curtail, you have to cut away some part of the PV, potential PV production, and this could be partly avoided if you have a higher share of technology that offers storage that can shift the total available solar energy to more demand, and thus avoid this problem with curtailing of available energy. Now, just a short overview on the macroeconomic impact on solar CSP in Spain. This was a study done by Deloitte, which shows that the initial premium paid by the state or by the customer of 185 million euros are outweighed by the contribution to gross domestic product of nearly 8 times more, plus additional fiscal ingressives for the government, and savings from replacing important fossil fuels. And this is for the year 2010, where still only a relatively small portion of the whole capacity was installed. And therefore, the picture probably in these years would be even much better. And this shows that even though the cost that you can calculate per kilowatt hour in Spain is relatively high, right now the premium is about 28 cents. The cost, of course, is lower because there must be a margin for the companies, is to a very big part outweighed that it's money that in the end incentives the national economy. And this is well shown on the numbers of employees and the advantages for local tax and regional economical convergence. You have here also a breakdown of the development of jobs in this sector for the different activities in the construction of the plants, also in operation and maintenance. You can see how this number is growing through the last years. And also, I think an important advantage or an important issue that has been achieved in Spain is that in the beginning there was still a relatively high share of foreign participation in the whole value chain, which now has come to a situation that in many of the different segments of this technology, the share of Spanish companies and Spanish development is much higher, so that the total share in the economic benefits also for Spain is very high, which always has to be compared to favorably compared to the cost situation. So the total local content here grew from about 50% in the beginning in about 2007, 2008 to now about 80% according to these figures. And this is just brief overview on the great value of solar thermal electricity, which is the same as CSP. It's dispatchable, it can support intermittent renewable energy technologies, and we can expect that the cost will decrease considerably when there will be similar numbers of installed capacity like we have now in wind and in PV, which are quite ahead in the cost development curve, of course. And the local content of STE plants is normally very high, which is also an advantage here. And with that, from Luis Crespo, from my colleague from Spain, just to resume on this main assets of concentrating solar power. And in the final slide here, you see also the roadmap of the International Energy Agency that predicts, on the one hand, cost regressions to come down to below 10 cents on the long term, and on the other hand, an increase of production that should give CSP in the year 2050 about 11% in the global share of electricity supply. And with this, I would like to come now to my last slide. Just give you an overview on the Solar Paces network, where South Africa is also participating. The Solar Paces is also developing, for example, standards and giving support to the development of this technology worldwide. And as a part of this activity, we're organizing an annual conference. The next one will be in Marrakesh in September, and it will give you a lot of overview on recent and detailed developments, and I would like to invite you very much to assist to the conference and to see you there again.